The Mandingo style takes a strong back and total breath control. If properly mastered, one's skin becomes impervious to swords, spears, and fire, even bullets. Ultimately, one becomes invincible.
I like to see if you can match my deadly Shaolin technique.
Like this.
Right!
Chef sharpens blade. Scorpion strike.
You bastard!
Oh, shit!
Time dilation is the apparent stretching of time near the presence of a black hole. Now, time cannot change direction or reverse, but it can compress and expand according to general relativity, which means that you can't travel backwards in time, but you can theoretically travel forwards in time if you experience 1 year as a second and somebody else experiences a year as a year. You're not actually time traveling, you're just compressing or expanding time to change the relative difference. Time dilation is famous for affecting the observers near a black hole. However, it also shows up everywhere else in the universe, anywhere where there is a gravitational curve. Like, we can use the gravity of the sun to observe galaxies behind it, because the light coming from it dilates and moves with the curvature of the sun. And in fact, even our GPS signals are a little bit dilated, and if we didn't correct for that, we would have very inaccurate data. The tiny amount of time dilation that affects GPS signals is caused by the fact that we are a little bit closer to the Earth than GPS satellites, and so we experience gravity a little bit more. But anyways, what actually causes time dilation? Well, I mentioned this in my simulating a black hole video, which you should go check out if you haven't yet, but I'm just going to assume that you didn't, and give you a brief rundown of the basics. When waves of light approach the event horizon of a black hole or any extreme gravity, they have to work harder to escape it. Now, when light has to quote-unquote work harder, it really means that it's losing energy. Now, a light with a lower energy means that it has a longer wavelength, and so when light approaches extreme gravity and escapes it, it redshifts greatly. Light is also redshifted from distant galaxies because of the expansion of the universe, causing those wavelengths to become stretched out. But that's a different topic. Now, you probably think of time as like this universal independent force, that's marching everything forward. But in reality, time is only how you describe it. If the universe had nothing in it, and nothing changed, and nothing happened, how would you define a second? There's no defining moment where nothing turns into nothing, There's no, outside clock that's counting down. The only way that we know time has passed is through things that we observe. So, looking at clocks or digital time machines, or before then, we would observe the Earth's rotation around the sun, or even our own conscious experience kind of counts time down. And as we age, we can count down the years based on how tall we are, or how gray our hair is, stuff like that. But without any of those observances, it's impossible to tell what time is. I mean, you can count down time in your head, but you're still using your brain to do that. Well, the tricky thing is that all actions and forces in the universe that we use to measure time are based on forces that run at the speed of light. For example, with the Earth's revolution around the sun, you might say that timekeeping is gravity. But in reality, you wouldn't be able to tell if you didn't have light being beamed into your eyes. And light moves at the speed of light because it's the electromagnetic force. Atomic clocks use the vibration of individual atoms, and those are all held together by the electromagnetic force. Even your own cells run on chemical reactions mediated by the electromagnetic force. And the things that aren't the electromagnetic force are either caused by the strong or the weak nuclear forces, which run at the same speed and under the same guidelines. So when you approach areas of extreme gravity and all of those forces get redshifted, you actually experience time in a redshifted kind of a state, because the amount of time it takes for a photon to cross from one atom to another in a cell in your body takes longer. And this isn't some like mystical thing. There is no universal time force. It's just mediated by whatever the relative speed of light is. And so you can say that your perception of time from near the event horizon is less real than somebody outside of it. A Schwarzchild black hole is the simplest theoretical model of a black hole, and is simply just a specific mass confined within the region given by the Schwarzchild equation that forms a black hole. So Schwarzchild black holes don't have any charge or spin. You don't account for Hawking radiation or cosmic microwave background. It's just a simple black dot hole. Just a mass. Now, the Schwarzchild metric was derived in 1916 during World War I, and it was the simplest model of a black hole to be realized. And later, different scientists would come along and add spin and radius and charge and all that weird stuff, but Schwarzchild's initial black hole was just a simple singular mass with a radius. LIGO, or the Laser Interferometer Gravitational Wave Observatory, is a pair of two physics observatories that both use 4-kilometer long vacuum tunnels to measure minute changes in gravitational spacetime. Its most famous discovery was in 2015, when it detected the gravitational waves put off by two black holes orbiting each other. Now, before then, we didn't really know that black holes existed, so this was a major discovery. It's also detected neutron star mergers and neutron star black hole mergers and other giant scale gravitational phenomena throughout the universe. Now, the two sites in Hanford, Washington and Livingston, Louisiana were constructed between 1994 and 1995 and finally opened in 2001. They later had an upgrade funded in 2008 before their major discoveries of the neutron star collisions and black hole orbits. The most recent interesting discovery that they made was in 2020 when they observed a very large mass, about 2 times the mass of our sun, being absorbed by a black hole about 25 times the mass of our sun. And this was really unique because we don't really have any evidence, and it's very hard to simulate large objects engulfing tiny ones because they tend to produce such tiny effects. Interestingly, this collision also wasn't detected by any light telescopes, simply just because it was too far away and too dim, but it was detected by LIGO via gravitational waves. And sadly, the founder of LIGO, Rainer Weiss, passed away at the age of 93, late in 2025. Now, in my Simulating a Black Hole video, I did a very in-depth explanation of Hawking radiation. If you've already seen that, feel free to skip ahead to this timestamp, but I'm going to explain it for the people who haven't seen that. Now, before we discuss Hawking radiation, we first need to understand quantum fluctuations. The core idea of quantum mechanics is that particles are not just singular point-like things that are moving around, but instead are just instances of a global wave function. You could think of it like a universal blanket that stretches out in every possible location in the universe. And where there is a particle, there is a peak in that blanket. So for example, an electron is not this single point-like particle that's physically moving around an atom, but instead it's a perturbation in the electron-flavored blanket of the universe that happens to be in that location of the atom and is moving according to the laws of motion. This also helps to explain how particles can be in a superposition in multiple locations or multiple states. They just exist as multiple different wave functions at the same time. So instead of poking up out of the blanket a lot in one spot, you poke out of it half as much in 2 spots. And that is represented as a superposition of particles. Now, every type of particle has this universal blanket, and there is a location in every point in space that this blanket presides, even if there's not a particle there. So the vacuum of space, even if there's not any particles in it, is still filled with all of these fields. They just happen to cancel out to equal 0. Now, as I mentioned, according to quantum mechanics, all particles are just expressions of waves. So this isn't exactly accurate, but you can kind of think of vacuum fluctuations as these little pairs of positive and negative particles that appear out of nothing and immediately cancel each other out. So the net gain in energy is nothing and the vacuum remains 0. However, those particles or waves are still there, and you need to account for them. Typically, quantum waves do not change in wavelength or frequency. I mean, it would be really weird if like you shined a flashlight and depending on which location and direction you pointed it so that gravity affected it differently, it like shone different colors. You know, that doesn't happen. The color of the flashlight or the frequency remains the same. Except for in the presence of a black hole, because of course they do. Everything gets really weird in the presence of a black hole. Now, the event horizon of a black hole is the point where gravity becomes so extreme that light has to work infinitely hard to escape, and that causes them to lose energy. Now, less energy in a wave correlates to a longer wavelength and a lower frequency. It's the same principle illustrated by the Doppler effect. If an ambulance is moving away from you, the sound waves have to work harder to reach you, and so their wavelengths become longer, which is what causes it to have a lower frequency and sound a lot more boomier than if it's approaching you, and it doesn't have to work as hard, which causes it to have a higher frequency and it has a lot higher pitch. As I mentioned earlier, typically the positive and negative energy vacuum waves cancel each other out to become 0, so that you have a net vacuum. However, in the presence of an event horizon, those waves can become redshifted due to the same principle, and that can cause the waves to become misaligned, which can lead to destructive or constructive interference. In a way, as a metaphor, it doesn't work exactly like that, but that interference and misalignment of waves can form particles. Now, those particles are created and emitted outside the event horizon of a black hole, and that is called Hawking radiation. And the energy that those particles release is equivalent to a black body radiation spectrum, which means that it has a temperature, weirdly enough. Now, this temperature is ridiculously tiny, and I'll discuss that later, but it is the exact same kind of temperature you think of like your kitchen stove has. It's just very, very tiny. The issue is those particles are being created out of nothing. You know, they're coming straight out of a vacuum and turning into real physical particles. That violates the conservation of energy, the conservation of mass, the conservation of information. Black holes have to pay that quote-unquote debt, which causes them to lose mass and energy over time. The details on exactly how and why black holes have to pay for that energy debt are a little bit fuzzy. In fact, a lot of this is very theoretical, but that's basically the gist of what Hawking radiation is. It is a thermal spectrum of emissions created by a black hole that causes the black hole to lose mass over time. A very, 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 very long time. In fact, the amount of energy a black hole releases is proportional to the mass that it loses times the speed of light squared. Assuming a black hole is not absorbing anything and is just sitting in pure vacuum, it will grow way faster than it shrinks due to Hawking radiation, just from absorbing the cosmic microwave background. That's only like 3 Kelvin. That cosmic microwave background was created right after the Big Bang and is just like a tiny, tiny amount of energy. But even that's enough to offset it. But yeah, anyways, the temperature of Hawking radiation is proportional to the inverse of the black hole's mass. This is because the more mass a black hole has, the further the event horizon is from the center, so the curvature along the event horizon is a lot weaker. And a weaker curvature leads to less redshifting, and therefore less Hawking radiation. So giant black holes emit very, very little radiation, but towards the end of a black hole's life, it will emit a lot. The Schwarzchild radius is simply the equation that tells you what size you have to shrink a given mass to turn it into a black hole. So, for example, the Schwarzchild radius of the Earth is about 8.87 millimeters, which means if you shrunk the entire mass of the Earth into the size of about a peanut, it would become a black hole. On the other hand, since the Sun has a lot more mass than the Earth, you would only have to shrink the entire mass of the Sun into a radius of about 1.9 miles to turn it into a black hole, which on a cosmic scale is still extremely tiny. A typical black hole mass has a Schwarzchild radius of thousands of miles. And supermassive black holes can be on the scale of thousands of times the distance from Earth to the Sun in radius. I don't know why I was using miles earlier, but for example, Sagittarius A star, which is I'm going to say this again for like the 10th time, but it's the black hole at the center of the Milky Way. From now on, I'm just going to say Sagittarius A star because I assume you know what I'm talking about. But anyways, it has a radius of about 12 to 13 million kilometers. Now, a Schwarzchild radius only accounts for a Schwarzchild black hole, so it does not include spin or charge. There are equations, specifically using the Kerr-Newman metrics, to describe spin and charge because they change the radius of a black hole. However, we'll get into that later. Tidal forces, aka spaghettification, yes, that is a real scientific term, is the effect where under extreme gravitational pressure, the object side that is closer to the black hole experiences stronger gravity than the side that is away. So let's say that you're being sucked in, your feet would be closer to the black hole than your head. So your feet would experience more gravity and would thus accelerate towards the black hole faster, causing your feet to move faster than your head and you to be stretched out. But stars and other large objects also experience this. It wouldn't just be a human being spaghettified. If a star crosses its path, the star is also spaghettified. It's just a star being spaghettified is a lot more intense than a human. And it emits a ton of radiation and supernova and gases, and it goes crazy. Similar to time dilation, tidal forces are actually weaker on larger black holes because the curvature near the event horizon is a lot smoother. And in fact, with supermassive black holes, you probably wouldn't even notice once you cross the event horizon, because the effect would be so weak. The maximum distance that a smaller body can approach a larger body's gravity without being ripped apart or spaghettified is the Roche limit, and is applied in all kinds of other things besides just weird black hole shenanigans. I mean, tidal forces are a real effect for any body in space. It's just they become extremely apparent in black holes, because the difference of your head and your feet in gravity is thousands of times. A galactic nucleus is an extremely bright spot at the center of a galaxy caused by a supermassive black hole. Now, when different gases and mass and particles and stuff approach a black hole, it is accelerated as it orbits around the black hole at extremely fast speeds, and that acceleration causes a lot of heat and friction. And so black holes tend to form these glowing bright accretion disks just outside of their event horizon, because anything that passes the event horizon gets sucked in. But matter can exist if it's traveling fast enough just outside of it. Now, supermassive black holes like the one at the center of the Milky Way are so huge and have so much mass sucked into them that they emit a disproportionate amount of light. And in fact, the light emitted from Sagittarius A star, which is the one at the center of the Milky Way, makes up about 0.1% of the entire light of the Milky Way, which is kind of absurd if you think about it. I mean, one single object making up 1/1000th of the light of an entire galaxy. And the final item on layer 3 of our iceberg is relativistic jets. Now, relativistic jets are extremely powerful beams of plasma that shoot out unidirectionally from a black hole. They primarily show up in charged and spinning black holes, as their magnetic fields cause the dust and gas in the accretion disk to kind of coalesce into the center and spit out a beam. Now, these jets can accelerate matter outwards, often thousands of light years, and are made up of ionized plasma. The matter emitted out of these jets approaches the speed of light, as the magnetic field is extremely strong on the event horizon of a black hole. Now, there are various different kinds and causes of these jets. However, the ones formed by supermassive black holes are considered to be some of the fastest and most energetic moving particles that we've observed in the universe. The reason they're called relativistic jets is because the particles are moving so close to the speed of light that they experience relativistic shifts in brightness and other weird general relativity effects that you would not typically see if they were moving slower. If one of these supermassive black hole jets were to hit Earth, the planet would be immediately and totally destroyed due to the intense radiation and extremely high energy particles. It'd be gone. It'd be gone pretty much. The collision would have about as much energy as 1 trillion times the amount of energy the Earth consumes every day. Well, that wraps up the third layer. I was originally going to do 2 layers in this video, like I did with the last part. However, I don't really want these sections to be longer than about 20 minutes, so that people still have time to watch them in chunks. But yeah, thanks for watching, and see you.
Entropy.
I can't quit you.